Hello, everybody. I will address the big data. I work in Moscow subway system. We have the center of unmanned transportation development, and we will talk about contemporary approach towards the management of big data in AI and big data time. So why are we talking about unmanned trams in this respect? Well, technologically speaking, this is a very difficult product, unmanned vehicles, but by the end of this year, we plan the launch of our tram. On one of the routes, it is equipped with advanced sensors, such as radars and cameras, about 4 radars, lidars, 6 cameras, which allows it to localize in real time and to locate itself in the city. It also allows it to find all the other participants of the traffic and to make its own decisions based on the environment. That is to say, what it has to do and where it has to go.
Такой технологически сложный продукт собирает большое количество данных.
As you understand, a technology-intensive product like this must collect a lot of good data. We can collect up to 70 megabytes of data per second, just a lidar, and there are several of them. We also have radars and cameras, GPS and other devices. They all collect the data, and it needs to be analyzed in some way. If you consider this data collection, then it must be marked up in some way, because for machine learning, it needs to be tagged. If it's clear how to tag data from cameras, but the data coming from lidars and radars are quite sparse. They represent points in space, and it's difficult to say which object you're talking about. It's still quite a work-intensive process, and one needs to cope with it somehow to minimize the cost of data collection and minimize the workload on its tagging annotation. So what are the main reasons? Firstly, you need to identify all members of traffic, which category they belong to, where they're moving. Especially important, it is to build paths or trajectories of movement for non-cars, like pedestrians or scooter drivers. That can behave unpredictably on the road, at pedestrian crossings, and they can present danger for themselves and for those around them. So it's important for us to be able to collect this kind of data. Not all the data that we're collecting can improve our models. In the traditional approach, we collect data. For instance, we have a route, and we spend 8 hours a day driving along this route. And then we can use this data to tag the data, but it doesn't work. In order to tag all the data, you need to view it all, and it takes quite a lot of effort. This approach is not scalable. We can't afford going about this way. So what are the approaches to avoid tagging or marking up all the scenes? That's, for instance, an approach based on location. Knowing that the tram at a certain point in time is at a crossing or at a stop, we're saying that we're going to collect the data based on geolocation. So we carve out a 20-second long scene. Or we can say say, let's do it by time. Let's see if it's peak time or not peak time, and see how passengers behave at this time and what passenger traffic flow we observe at the street at that time, or in the morning or in the evening. Also, we can consider stratified sampling, where we have to understand what's happening at a certain in a certain season or at a certain weather, what happens on the rain or when it's snowing. And perhaps the most important kind of sampling is event-triggered. It's about those events that happen unexpectedly. For instance, the driver has overridden the control, pressed the brake button. It's important for us to understand why they did so, and based on which data the model took a decision that either something needs to be done or the person has taken this decision. So, considering the traditional approach to training, we collect big data from the 8-hour route. We split it into small pieces, and we add data from lidars and radars at our cloud storage. Later, we can get data from the in response to our requests, and based on the sampling strategy chosen, we pick and load the data. Then we can send these 20-second scenes for the markup. Data gets to the label studio, and radar and pen cloud data gets to the CBUS, where the markup agents are doing that either with 2D bounding boxes or 3D bounding boxes. Later, the marked up data needs to be verified. We have validated the check how well the data quality meets our requirements for machine learning. They go to clear memory, and we control versions of these data so that we can understand how well our data behave compared to the current data. And then we can run experiments on our ML platform. This way, we get an interactive process. We add data, we build a machine, and deploy our models. In this case, a problem arises. What data to choose? And I mean, if the data volume keeps growing, so the process doesn't scale very well. In this case, what can help us is the so-called active loop learning. What's the gist of it? So that our model itself would pick. The model says she's not sure about certain samples, and then we can send these samples directly for the markup. If in the current version the model says it's not sure, a certain cluster is collected based on this data, it's sent to the sampler, and the sampler decides whether it should be sent for markup. In this case, the quality of our data improves, because not all the data is worth sending for markup. So what cases needs to be considered? In the current situation, we need to choose which metrics are not good enough, and we need to improve them. We have to set the threshold confidence. So we have this average confidence, less than 60%, for instance. In this case, we say that the model, we're not confident enough about the method. Also, disagreement metrics can be used. So if several models disagree, then we need... Well, it says that this data does not exactly fit the current model, and we need to improve the data to meet the current metric. Later, a decision may take to use VLMs and MLMs and LLMs to further improve our data. So if, for instance, we have a demand of certain data, for instance, we have a great disbalance between classes, too few trams or kids or bicycle drivers, you can look for the required data in the 8-hour bag to carve them out to improve the quality of the metrics. So how does the pipeline look if we use the so-called active loop learning? In this case, the model is trained on initially a small set of data. Then it's run through non-marked up data. After we've got some metrics, we say that they need to be sorted and to choose the less confident ones. And the most confident ones we're sending for markup. After the markup, we send them back to the selection, and we get into this kind of loop. We supply new data all the time and allow the model to choose in those cases where it's not confident new data, and it becomes more robust. Does active loop learning really help in training our model? If you take a look at our metrics, you can understand that nuisance, for instance, when being learned on only 70% of data, allows achieving map metrics up to 72. But if we use the entirety of data, this metric achieves 83. So one can confidently say that using just half of the data that the data wasn't sure about can allow us achieving quite a good metric. One can say, why must one use half the data when one can use 100% of the data? But in the current situation, when I have a tram, we don't have 100% of data, and we don't know what this 100% is all about. For instance, in new scenes, there are about 3,000 scenes. It's difficult to say whether it's too few or too many. I saw data sets including more than 100,000 scenes, and the data keep being added. It's difficult to say how much data you need to improve the quality of our model to a certain level. So therefore, you need to keep selecting the scenes that we need and improve our metric.
Так, а видео не запустилось.
The video isn't running. Well, a GIF file should have worked here. So basically what it's all about, if you take random scenes, it means that quite a lot of objects can be absent. If you take this picture of the cloud, you can see 3 cars there. So the data is quite sparse. No objects are seen. But because we don't have enough targets, it leads the model to degrade. So therefore, we need to select those scenes that have the largest value for us. So when we were selecting in a random way, we picked a bridge where there's no data that's valuable for us. So we need to approach the object selection in a more in a more appropriate way. In this case, large language models or multimodal models allow us doing data pre-markup or finding those classes that we'd like to find to improve these balances. For instance, you can add people, and the model would be able not only to identify people but also to segment them. Like in this example, we're saying that we want to find people, then the bounding boxes are sent to SM2 and segmentation of the model is happening. Here, a pre-trained model, a so-called foundation model, can solve this problem for us and even do the pseudo markup, segmentation markup. That's actually quite work-intensive. I mean, to identify pixels of different colors. It appears that using large language models, we can build a data set, for instance, to ask questions so that it should describe a scene, and then to find the scenes that are of interest to us based on the text prompt, or to set visual question and answers. Like, for instance, we're asking how many people are there in this picture, and it could answer not exactly accurate, but in most cases roughly accurate. That would allow sending it for validation of whether we need to send this data further. And of course, image search. We can feed some scenes and try to find. For instance, we have a day-like scene, and we'd like to find similar scenes using embeddings, so as not to do it manually based on geolocation, because geolocation is not always accurate, especially these days. So to correct for that, so we can use this approach. In this case, we see our pipeline changed a bit. So now, in order to identify random scene instead of identifying scenes by geo marks, we use VLM. So it would calculate the possible path and select the scenes so that we should understand if it makes sense to mark up those data. So the pipeline changed. Instead of 3 pre-training phases, we get 4 pre-training and training. The training, query, and to find the new data, and then this new data adds to the current data. So unfortunately, I won't be able to run the video here again. But why? This one was supposed to show why we need data. A person was running across the picture here, but unfortunately we can't see it. So the situation is like that. The tram stops and the person is running to board it in a not allowed place. This data is very valuable for us because it's an accident-prone situation. As you can see, it's quite difficult to mark up these areas. It takes a long time to get used to understanding where a person is, or where a bike or a scooter is, or kick bike is. If active loop learning helps you, then why VLMs are needed? This one shows that motorcycle lie on the road is a perambulator with a confidence of more than 50%. And if you take across the scene, it turned out to be more than 60. And then it won't get into our selection. Then you can ask a question to VLM: is anything strange happening on the road? And it will correctly say there's a bike lying on the carriageway, and there are cones around it, which means that an accident happened. So these models can really help you identifying those situations that you can skip or miss using active loop learning. Also, using multimodal models, we can send a whole video instead of a single picture, and based on the video we can learn asking questions. For instance, we ask how many people are there on the bus stop. Our model says 2 people, but if you take a look on the right, indeed there are only 2 people. And it also says, yeah, it's going to happen next. And it can also output the so-called timestamps. We can ask a question, at which time range do we see a blue bus? And the model gives the correct answer between seconds 10 and 11. If you take a look, indeed, it's at that time range that the bus starts appearing on the right. So basically, language models and VLMs help speeding up our data markup.
If
you take a look in general, then you can see that using active learning and VLMs, we can reduce the number of data required by 30 to 70%, depending on the metric we want to achieve. And more likely than not, the drones will be using end-to-end. So there will be different. There won't be different models responsible for perception localization, but there will be one linguistic model that will be responsible for planning, motion, locomotion, and detection. As you can see, the reasoning is happening on the machine, and it's asking which actions needs to be taken. On the right, you see that construction work is happening, the road is being repaired, and the machine decides that one needs to change to the left lane in order to avoid a situation in the future. In conclusion, I can say that indeed some visual models and active learning can indeed help speeding up data processing. They can also improve the quality of our model because we may use them to effectively train and to teach our model. This process becomes more scalable and more intelligent. So through going away from manual data selection, but allowing the model to do that, we can achieve much better performance. Also, the use of LLMs or VLMs or multimodal tools, we can check we can correct for the class disbalance problem. That's all I wanted to say. Thank you. Thank you, Renat. Exciting. Colleagues, let's try and ask a few questions. Okay, one in the center of the room. Hello, thank you for your presentation. Can you please... Well, I actually have two questions. First, which LLMs have you used? Did you have some open source LLMs, just as a matter of by way of advice? And the second question, it appears that you already use VLMs. So what is the percentage of a manual markup that went away once you started using VLM, or you gave up on manual at all? In the current situation, the way things stand now, people say that the SAM model that has been released can mark up with a higher quality than a human. So humans mark up very well in 2D, but when it's about 3D, with data from radars or lidars, the data is very sparse, and either VLMs or LLMs don't really work very well, so you can't go away from labeling. And also, in pseudo-labeling, it's indeed important to make sure that it really works. They come here, see that everything is marked, and then they say one shouldn't do anything about that. And you have to be very careful about that, because it looks we needed to get data pseudo-labeling, and the labelers didn't work. They just corrected something. So going away from human intervention is not possible at all. As to the models, in the current version we use Quen. It's a Chinese model from Alibaba, I think. Then there's a Chinese open source model. I won't be able to recall right now off the cuff. Llama? Ilama? No, not Ilama, no. It's from the OpenGL lab, the Shanghai lab. They had quite a good model. You can come up and I'll show it to you. Thank you. Colleagues. Another question. Thank you for your presentation. It's been extremely exciting. So I have a question. If a driverless tram is moving, and then I see it from 30 meters and start running, will it wait for me? Well, I think hardly. It will follow the schedule. If it has a time planned for the schedule, it will stay at the bus stop. If it's lagging, then I don't think it will act as a human driver to wait for a person running to board it.
Вот тут, скорее всего, он не тронется, это точно?
Well, in that case, it won't start if the person is already on the step. Okay, thank you. Thank you for your presentation. I have two questions. One about lidars. As far as I know, they don't work in fog or rain. So will your trams just stop, or will they rely on other kinds of information? Who's cleaning those lidars? Or do you have a special person to run before the tram to create accident-prone situation to improve the model? Well, actually, lidars can see.
Если так смотреть,
well, if you look, in some weather conditions, they still see. But we have backup sources, cameras and radars. So radars will cope with some metal objects, cars, but others are controlled by cameras. It doesn't mean that we don't have a backup set of sources. We have data fusion models based on multimodality. By adding all these three modality, we can predict if there's an object on the way or not. As to the dust on the sensors, yes, it is a problem, but we are not really working on it right now. All large companies are solving it in some way. For instance, they look at the camera and need to decide where cleaner, it's time to clean it, or after the cleaning we need to dust off the water as such. So indeed, so a problem like that exists, but we're not yet working on it. It's just before each departure, you have to make sure that the sensors are in good condition. Let me just add, in terms of creating or not creating a test situation, one colleague of mine has a great phrase. So life-wise, it's more complicated than a real-life situation. So what you get from roads is clearly more sophisticated or complex than the real-life situation. My name is Lad. Thank you. My question is about the security of machine learning algorithms. In public transit, in self-driving transport, it's extremely important. In order to teach a model, you use different data modalities, lidars, GPS data, cameras. Do you apply any algorithms to protect your model from a person, for instance, who will decide to stand near the tramway with a plaque with a sheet of paper showing some alternative situation? You know, as every system, it has to have several contours backing each other up. You can't rely just on the lidar or on the camera. There's an additional algorithm, so you can use a point-based algorithm. If you manage to cheat the lidars, for instance, pointing a laser beam at it, some other algorithms will use. If some sensors break, data spoofing occurs, and the machine must take a decision that it's better to stop, because otherwise it's not clear which actions needs to be taken. So all models, all the backup models needs to go through a test based on the test data, and we have these test runs where we do that. Also, we have a simulator. We can simulate what happens if a car stops abruptly or a pedestrian steps on the road. So it looks that we can model all the extreme situations, and based on them, make a decision of whether indeed our model is safe for the current situation or not. Got it. Thank you. Colleagues, yes. We still have questions, maybe a couple more questions. Thank you for your presentation. I remember from augmented reality that they say that there are two processes. One is the detection and the other one is tracking. And response speeds are different. I guess you must have something like that. So what kind of speeds you are supporting in terms of detection and maintaining objects? It looks that if you take a look at maintaining or following the object, it works quite fast because it doesn't use any neural networks. You can use some Kalman filter, for instance, just to sort things out and attract the closest points from the previous prediction. Here, you don't need to worry about the speed regarding the tracker. As to detection is the main consumer in time, but it runs within milliseconds in our case. I can't give you an exact number, but we get it working quite fast. The question there is more about not how long one perception runs for, but the whole system, because just any system works on ROS, and there are a lot of nodes in the ROS, each of them responsible for their own action. If taken in sum, it fits within the parameters of human perception. So in time, the response time is much better than a human driver would respond to a situation. Okay, got it. And how do you explain why the model has taken this particular decision? I'm asking about the decision interpretation. In the current version, unless you use VLMs or you just get perceptrons or transformer models, the situation with the interpretability is quite difficult. You need to build some heat maps and try and analyze why it happened this way, not the other. Sometimes it's about some classification. So a person has become a bicycle driver. So such moments are difficult to interpret. In these cases, in order to improve the interpretability, you need to change the model, for instance, to add some heads, so it should predict add some text for every predict. In that case, we can understand based on which the model has taken this decision or that. In the current version, unfortunately, we don't have this interpretation. One can apply interpretation for 2D and 3D. It's very difficult, and basically there's too little research in that area. And of course, it's worthwhile working in this direction to understand why the model is taking certain decision. So far, it works like a black box. So yeah, there's a certain problem with interpretability.
Okay, so the final question. Okay. There was a question here. Please try to be short. Thank you for your presentation. Talking about efficient data sampling, are we going to take into account that each element has less than zero chance to be or rather more than a zero chance to be selected? Sometimes they will not be selected at all. If you look at some projects, there will be cases when an object will not be detected at all. Let's say somebody which is lying on the ground as a motorcycle, for instance. In 3D, it will not be detected as an object. It will either be something unknown or will not be detected at all. So therefore, more than zero, I don't know. There is a chance that it will not be detected. There are some hard cases, right? Difficult cases. That is to say, it's not kind of one pill approach. It's not like we're going to only use one algorithm and everything will be all right. No, I don't think this will lead to a good decision. If active learning worked that well, everybody would teach it. Everybody would use it, but I don't see it working that well. Well, Renat, thank you so much. If you have more questions to Renat, and I know there are, you can do it offline. Okay, and traditionally, the prize for the best question goes to cognitive learning. I think this was the most difficult question for me. Would you please approach the stage? Thank you for your question.